Hello, I welcome you. The problem reads the train consists of a 50 megagrams engine and 3 cars, each having a mass of 30 megagrams. If it takes 80 seconds for the train to increase its speed uniformly to 40 kilometers per hour starting from rest, determine the force T developed at the coupling between the engine E and the first car A. The wheels of the engine provide a resultant frictional tractive force F, which gives the train forward motion, whereas the car wheels roll freely. Also determine F acting on the engine wheels. This problem is coming from the Engineering Mechanics and Dynamics, 14th edition by R.C. Hibbeler. Okay, so now what do? We are using the principle of linear impulse and linear momentum, which is F equal to delta T is equal to M delta V. And this is a vector quantity, and by that we mean it as direction and magnitude. So what do we have here? So we have F here. The question is to determine the force F as well as the coupling force T. So delta T equal to M delta V. Our delta V is equal to V final minus V initial, and our V final is equal to 40,000 meters divided by, we want to convert this to meters per second. This is meters per second. Okay, what else? And so we need to find F. All right, finding F, we'll say F, okay, and our delta T there is just equal to 80 seconds. So this times 80 is equal to the mass. Our mass here is 50,000 kgs plus 3 times 30,000 kgs, then times delta V, which is 40,000 divided by 3,600 minus V naught. Then we calculate what F is. So we have 50,000 plus 90,000 times 40,000 divided by 3,000 and divided by 18. So this we get a 19,444.444. So this is 6. Okay, let me write this properly. Okay, this is 3,600. So this is our F. So now let's isolate this part alone, so that we work on that coupling force. So if we are to isolate the head, the engine alone, there we go. Okay, so we have the weight, we have the force, and then here we have the coupling force T. So this is T, this is W, which is just equal to 50,000, okay, by 9.81. This is F. And then we have the normal force. We do have the normal force also. Yeah, like so. Alright. So applying this equation again, so we'll say f delta t is equal to m delta v. Okay, so our f here, we already calculated it, is 19,444.444. This is in newtons. And then we have delta t, it will still remains 80. Then we have m, which is just equal to 50,000 kgs. Then we have delta v, which is just equal to v final minus v initial, and this is equal to the same 40,000 divided by 3,600 minus 0. So if we are to feed everything in that equation, then we have 19,444.444 times 80, and this is equal to, our t, so our f here, f is going to be equal to, f is equal to, so if we are to sum up these forces, so motion is in this direction, this is motion, it is in this direction. So this equation instead becomes not just f there, it becomes f minus t. Okay, so then we'll have a 19,444.444 minus t, then times delta t, which is 80. This is equal to the mass, which is a 50,000, just a head alone, then times delta v, which is 40,000 divided by 3,600. Okay, just minus 0. And therefore, making t subject to the formula, which is the coupling force, this we are going to have, that's 40,000 times 50,000 divided by 3,600 divided by 80. T goes this side, the other one, so this one will say like so, plus 19,444.444. Okay, so T therefore just becomes, say, 12,499.99, which is just a 12,500 newtons. Okay, so this is our coupling force. This is our coupling force for this particular problem. Alright, so I hope this particular video was helpful. I hope it was helpful, and if it was, give me a thumbs up, like my video, continue subscribing and liking my channel. Of course, also we are taught to calculate f, and this is the value of f here. Alright, I think this is about it, and I hope this video was helpful, and if it was, give me a thumbs up, like my video, continue subscribing and liking my channel. Bye bye, and see you in my next screencast.